The purpose of this screencast is to explain the qualitative conceptual features of a phenomenon called resonance energy transfer, one manifestation of which is something called fluorescence resonance energy transfer. This is a theoretically interesting and extremely useful phenomenon that's widely applied in various fields of molecular science and increasingly also in cell biology. The resonance energy transfer process the fluorescence resonance energy transfer process sort of naively looks as if a photon being emitted by some fluorophore is being absorbed by a second fluorophore with an overlapping absorption spectrum. And then that second fluorophore re-emits it at a lower wavelength because of the additional Stokes shift in the acceptor molecule. So again, the phenomenology is that you have a donor fluorophore, which has some kind of emission spectrum. If that emission spectrum overlaps the absorption spectrum of another fluorophore, what you see is that you get energy transferred from the donor. That energy transfer, of course, reduces the fluorescence of the donor, so there's a quenching of the fluorescence of the donor. If the acceptor species is fluorescent, what you get is then actually a fluorescence is not shown here in this diagram, but you get a fluorescence emission from the acceptor. So if the acceptor's fluorescence is fluorescent, the quenching of the donor fluorescence is coupled to the appearance of acceptor fluorescence. But resonance energy transfer will still happen when the acceptor is non-fluorescent. As long as the absorption spectrum of the acceptor overlaps, the energy will still be transferred. But if the acceptor is non-fluorescent, that energy just disappears. If it is fluorescent, it will reappear as fluorescence at a higher wavelength, lower energy, reflective of the Stokes shift of the acceptor of fluorophore, and that process is called fluorescence resonance energy transfer. Now again, naively, this could be explained by a fluorescent photon being emitted from the donor and then absorbed by the acceptor. And then, of course, once the acceptor is excited, it can be re-emitted as acceptor fluorescence. So qualitatively, it sort of looks like that, but quantitatively, you cannot explain it that way. If you use simple calculations to estimate the efficiency with which the photon emitted by a donor could excite an acceptor, you find that the actual efficiency of the RET process is tremendously higher than you can explain by that kind of radiation dependence process. So something else must be going on physically, and what's going on is a radiationless intermolecular transfer of energy mediated by the electric field of one molecular dipole doing work on another molecular dipole. So optically absorbing molecular transitions, as we've talked about repeatedly, have to have a change in the molecular dipole moment in order for them to be promoted by the electric field, for energy to be transferred into those molecular quantum states by the electric field of light. So if the molecule can absorb light, if it absorbs light strongly, it's always that process is always driven by the electric field of light, and that means if there's a strong absorbance, there is a change in the molecular dipole moment during that transition. So that means if there's a change in the molecular dipole moment, at least either the ground state or the excited state must have a dipole moment. In general, both of them have dipole moments, and of course the difference between the dipole moment and the excited and ground state is something we would roughly call the transition dipole moment. What RET comes from in the end is one of those molecular dipole moments interacting energetically with the other electric dipole moment, right? So the dipole moments, well, the electric dipole moment in the donor species is effectively pushing on and doing work on the electric dipole moment in the acceptor species. And by pushing in the right way in the electric dipole moment in the acceptor species, it can transfer energy and it can push the acceptor species into the excited state. Now, for reasons that would be hard to explain in detail, but that are consistent with that qualitative explanation, quantum calculations show that the resonance energy transfer, or RET rate, depends on the interaction energy of the transition dipole moments for the transitions exchanging energy between the two molecules, right? So for resonance energy to transfer to occur, you have to have you have to have a transition in the quantum state of one molecule. When we're working in the visible or UV range of the spectrum, we're looking at electronic transitions. So for RET in the visible range or UV range, we're looking at a transition between two electronic quantum states in one molecule, and that's somehow coupled to a transition between two electronic quantum states in the other molecule. So for that energy exchange to occur between those two molecules, basically swapping the excitation energy from the donor molecule into the, swapping the excitation energy from the electronic transition in the donor molecule to the electronic transition in the acceptor molecule, it turns out the rate of that is proportional to the interaction energy of the transition dipole moments. So again, this is a bit hard to explain in detail. The quantum mechanics established this to be true. Qualitatively, this is consistent with just the simpler concept of the dipole moments in the two molecules sort of pushing on one another. In practice, the RET rate is given by the dipolar interaction energy of the two transition dipole moments. So the probability of, well, in this case it says FRET, fluorescence resonance energy transfer, is given by the dot product of the two transition dipole moments, right? These are transition dipole moments, minus 3 times the dot product of the intermolecular vector with one transition dipole moment, and then the dot product of the second intermolecular vector with the second transition dipole moment, and all of that and then the probability of that is proportional to the reciprocal of the third power squared, because basically the dipole interaction energy is given by, well, the transition dipole moment interaction energy is given by this term in the parentheses. The probability of the transfer goes with the square of that value. When you square this term, you get an r to the 6th dependency. So the rate of the resonance energy transfer depends on the 6th power of the intertransition dipole moment distance. It depends on their relative orientation, right? Because the dot product has a term that would depend on the cosine of the angle between the dipole moments and the cosine of the angle between each of the two dipole moments in the vector separating the two dipole moments. Okay, so the RET rate depends on the 6th power of the intertransition dipole moment distance. Their relative orientation, the orientation comes in from these dot products that describe the dipole interaction energy. And then on the integral of the fluorescence emission spectrum of the donor fluorophore with the absorption spectrum of the acceptor chromophore, right? That overlap requirement sort of explained schematically here. Effectively, the strength of either the absorption or the emission at a given wavelength reflects effectively the transition dipole moment magnitude at that wavelength. And so effectively that overlap integral when you do all the quantum mechanical calculations, that overlap integral is reflecting something about the strength of the dipole interaction energy at the different wavelengths. Okay, and so an important thing in resonance energy transfer and fluorescence resonance energy transfer is something called the Foster radius. If you look at this equation, so we'll see later on that the rate of resonance energy transfer is proportional to the 6th power of something called the Foster radius divided by the 6th power of the Foster radius divided by the distance between the transition dipole moments, right? So r here is the difference between the distance between the transition dipole moments. That r and this r are the same quantity. We'll see that the resonance energy transfer rate depends on the 6th power of something called the Foster radius divided by the distance separating the two transition dipole moments. When you sort of crank through a little bit of math describing the relative rate of the resonance energy transfer process compared to the other processes producing de-excitation of the donor, right? So in the donor we can have fluorescence, we can have quenching of various kinds. When you look at the relative rate of resonance energy transfer compared to all those other processes, you get a rather simple expression. You get the Fred efficiency depends on the 6th power of the Foster radius divided by the sum of the 6th power of the Foster radius and the 6th power of the distance between the two transition dipole moments. If you look at this quickly for more than a moment, you will notice that if this distance between the transition dipole moments is r0, this equation simplifies to 1/2. So when the distance between the transition dipole moments is equal to the Foster radius, the Fred efficiency is 1/2. So RET efficiency, or Fred efficiency, is 50% for two randomly oriented transition dipole moments separated by the Foster distance. Important, sort of hidden point here is that to get this exact equation, you have to sort of integrate over random orientations of the transition dipole moments. So this principle of 50% transfer at the Foster distance does depend on the two transition dipole moments being randomly oriented relative to one another in the ensemble of fluorophores undergoing resonance energy transfer. So in all cases, the donor fluorescence is quenched by the resonance energy transfer, right? The energetic excitation in the donor, the energy stored in that electronic transition, the energy in the excited state in that molecule gets transferred to an electronic transition in the acceptor. So that transfer of excitation from the donor molecule to the acceptor molecule removes the excitation from the donor molecule. It takes the donor molecule out of the electronic excited state. Therefore, it can no longer fluoresce itself, and the fluorescence is lost or quenched. So whenever there's resonance energy transfer, the fluorescence is quenched. If the acceptor is fluorescent, when the transfer happens, the acceptor can then fluoresce. And of course, that fluorescence will be at lower energy due to the Stokes shift in the acceptor. And so the acceptor then will necessarily fluoresce at a lower energy of the donor. This will happen if the accepting molecule is fluorescent. And in that case, it's called fluorescence resonance energy transfer because the fluorescence seems to go from the donor and then appear as acceptor fluorescence. If the acceptor is non-fluorescent, you still get the quenching, and you could call that FRET quenching, or more properly, RET quenching. So in any event, when there's resonance energy transfer, the donor is quenched. If the acceptor is fluorescent, you will see that quenching manifested as fluorescence emission from the acceptor. And if the acceptor is non-fluorescent, you will only see the quenching of the donor. So that's sort of a broad overview of the phenomenology and its most important quantitative characteristic and its physical origin. We need to know a bit. It would not be a vast amount of sort of quantum mechanics needed to arrive this result, but it would probably be sort of a couple weeks of lecture for students at your level, and so we're not going to have time to do that. But again, the qualitative point is that the molecular dipole in one molecule is pushing on the electric dipole in the other. When it pushes in the right way, that electric force, that electric dipolar force, can do work on the acceptor molecule. When that work is done, energy is transferred from the donor to the acceptor. Because it's basically happening via a dipolar interaction, the probability of that is the strength of the dipolar energetic interaction goes as r to the -3. Because the probability of transfer is the square of that energy, the efficiency of the fluorescence resonance energy transfer power goes with r to the 6th. And so that captures, I think, all of the most essential features of the RET and FRET processes. So again, naively, it looks like emission of a photon by a fluorophore and absorption of that photon by another fluorophore, and then subsequent re-emission. Right. So this is usually described as donor and acceptor molecules. The donor fluorophore would be fluorescing, but it's again, naively, it looks as if the photon is being emitted from the donor, picked up by the acceptor, and then re-emitted by the acceptor. However, if you do detailed analyses of rates and of the physics of this, you learn that that is not true. As we'll show on the next slide briefly, this actually arises from a dipolar interaction between the different fluorophores, right? As we've shown, as we've emphasized earlier, for resonance energy transfer for an electronic absorption to take place using the electric field of light, the dipole moment of the molecule has to change. So a fluorescent molecule has a change in dipole moment, or a transition dipole moment, between the ground and excited states. So all fluorophores are characterized, all molecules that absorb light with any reasonable efficiency have changes in dipole moment that accompany the change in the electronic quantum state. And so actually what resonance energy transfer involves is energetic interaction of those dipole moments. And actually, for quantum mechanical reasons, it ends up being interaction between the transition dipole moments. And so that's a little bit complicated to see, but a simple way of thinking about it is that as we saw in the course of a vibrational oscillation, the dipole moment has to change continuously. Essentially, that means that as the molecule is vibrating, the dipolar field of the molecule is constantly vibrating. So that basically oscillating dipolar field can push on the dipole in another molecule. In that interaction of the oscillating dipole field in one molecule with the oscillating dipole in another molecule, effectively can cause them to trade energy by the electric dipolar field doing work. By the electric dipolar field in one molecule can do work on the electric dipolar field in the next molecule. And so in the end, what happens is that produces a transfer of the excitation from the donor, right? So this would be the emission spectrum of the donor. If the emission spectrum of the donor overlaps the absorption spectrum of the acceptor, what that means is that the emission energy is matched to the absorption energy. If the emission energy is matched to the absorption energy, then energy can be conserved when it is transferred between those two states, and that's effectively what happens. So for the moment, right, so the key points here is that resonance energy transfer involves basically interaction between fluctuating dipoles in the two molecules. The fluctuating electric dipoles. The electric dipole in one molecule can do work on the electric dipole in the other molecule. Ultimately, what enables light to produce an absorption and put energy into a molecule is, of course, work being done on the electric dipole moment of that molecule. In the same way that light can do work on the electric dipole moment in a molecule, a oscillating dipole in another molecule can also do work on the electron dipole in a molecule. So it's that energy transfer via dipole-dipole interactions. The fluctuating dipole in one molecule doing work and therefore trading energy with the fluctuating dipole in another molecule. That is ultimately when a resonance energy transfer comes from. And so it has a very steep spatial dependence because it involves the interaction of two dipoles. We'll come back to that in a moment. Physically, it is actually the transition dipole moments that are determining this interaction when you do all the quantum mechanics properly. But for the moment, we just want to focus on the point that when you have resonance energy transfer, it is another contribution to non-fluorescent emission, non-fluorescent removal of the energy from the donor. So when the donor undergoes RET, or resonance energy transfer, it can no longer emit a fluorescent photon. And so that is another rate that contributes to the total rate of removal of the electronic excitation from the donor. Don't worry about this lifetime thing at the moment, but down here again, the rate of fluorescence is going to be, the quantum yield of the fluorescence is going to be that rate, the fluorescent emission rate divided by the totality of all de-excitation rates. And if you have RET, that makes a contribution to the de-excitation rate. And so RET effectively quenches the fluorescence of the donor via the same kind of logic and math that we looked at in the previous slide. So that's an important point. RET quenches the fluorescence of the donor. So there's a loss of fluorescence of the donor. Now, if the acceptor is fluorescent, you can then get fluorescence and will get some fluorescence out of the acceptor. But of course, if the acceptor, but we know that there are many chromophores, there are many species that absorb light that are not fluorescent. If the acceptor is has a properly matched absorption, the transfer of the excitation energy depends only on the match between the absorbance spectrum, or the absorption of the acceptor, and the emission spectrum of the donor. Right? As long as the absorption spectrum of the acceptor is energetically matched to the emission spectrum of the donor, the same quantum mechanical dipolar interaction process can transfer energy between them. If the donor is non-fluorescent, it's because if the donor is non-fluorescent, it's because all of the non-fluorescent decay pathways in the, if the acceptor is non-fluorescent, when a molecule that absorbs light is non-fluorescent, it's because all of the non-fluorescent decay processes in the end are much faster than the fluorescence decay process. And so if resonance energy transfer happens to a molecule that is non-fluorescent, right, where all of the non-fluorescent properties kinetically outcompete the fluorescent process, the fluorescence of the donor will be diminished, and you will not get any fluorescence in the acceptor because it is non-fluorescent, but the resonance energy transfer can still occur and can occur quite efficiently, and it will quench the fluorescence of the donor. And the only requirement for that resonance energy transfer process, for that RET-based quenching to occur, is to have a proper energetic overlap between the acceptor absorption spectrum and the donor emission spectrum. Now, the length dependency here is quite an important property. We'll see that the efficiency, the rate of resonance energy transfer, scales with the 6th power of the distance between the transition dipole moments. A convenient way to quantify that is to define something called the Foster radius. If you look at this relationship, when the Foster radius, when the separation between the two particles is equal to the Foster radius, this term equals 1. And what we've done here is we've sort of scaled the fret rate according to the lifetime with no fret. Let's not worry about the mathematical details here for the moment. Actually, let's look for the moment just down at this equation down here where we've rearranged the math. I will have another screencast where this math is explained more clearly. But the bottom line point is that the efficiency of fluorescence resonance energy transfer, or even non-fluorescent, this could just be the ERET, the efficiency of resonance energy transfer, will be given by the 6th power of this Foster radius over the sum of the 6th power of the Foster radius and the 6th power of the distance between the transition dipole moments. So let's just look qualitatively at what this means, right? When the distance between the transition dipole moments is R0, right? Suppose this is R0. Let's just set this for the moment to R0. What do we get? We get R0 over R0 plus R0, or right, to R0, it equals 1/2. So this just shows that when the separation between the transition dipole moments is equal to the Foster radius, there's 50% resonance energy transfer efficiency. And so that means under these conditions, 50% of the, you basically reduce the fluorescence quantum yield of the donor by 50%. Right? So these equations are set up so that, well, the Foster radius is defined such that when the acceptor is at, when the distance between the transition dipole moments in the acceptor and the donor is at the Foster radius, you have 50% reduction in the quantum yield of the donor. And so there is a 50% efficiency of transfer of energy from the donor to the acceptor, and there is a 50% reduction in the quantum yield of the donor. We'll come back to that math later on. It is important to wrap your heads around it, but it's more important to understand the qualitative points, so we'll leave it at that for the moment. Okay, and this this gets a little bit more into the physics of the RET, or resonance energy transfer process. The probability of the resonance energy transfer event is given by is proportional to the interaction energy of the transition dipole moments, right? Delta D is the transition dipole moment in one of the species. Sorry, delta D1, delta D2. These are the transition dipole moments of the two interacting molecules. R is the vector between the transition dipole moments in the two molecules. And so this probability term, well, it's the square of something that is actually quantifying. Well, if these were just dipole moments, this would quantify, this would describe the electrostatic interaction energy between the dipole moments. And so in this formula, they're actually transition dipole moments. This is basically looking at the electrostatic interaction energy between the dipole moments. And what it's looking at effectively is the oscillation in the dipole moment, right? What's going on here is the electric field of a molecule is varying as its dipole moment fluctuates, right? We saw that in vibrational spectroscopy, as we go along the normal coordinate, the dipole moment changes. Therefore, the dipole, if the dipole moment is fluctuating, the electrostatic field of the dipole is fluctuating. That fluctuating electrostatic field, again, this ends up being, when you do all the rigorous physical calculations, you can show that this depends actually on the transition dipole moment. But effectively, what you're looking at is the fluctuation of the dipole moment in one molecule, producing then a fluctuating electrostatic field from that dipole. That fluctuating electrostatic field pushes on the dipole moment, the transition dipole moment in the other molecule. So the fluctuating dipolar electrostatic field in one molecule ends up being able to do work on the other molecule, changing its dipole moment, which of course involves a change in, which is what is described by the transition dipole moment, right? The transition dipole moment describes the change in the dipole moment of the molecule in the course of a transition. What you have is the fluctuating electric dipolar field of one molecule pushing on and inducing a transition that changes the dipole moment of the other molecule. And so the same way that we saw we needed a change in electric dipole moment for the electric field of light to do work and transfer energy into a molecule, we need a change in electrical dipole moment for the fluctuating electrostatic dipole moment in one molecule to do work on the other molecule. And so this is a non-radiative transfer process. Resonance energy transfer is one form of non-radiative transfer. Again, naively, you could view it as a photon being emitted by the donor and absorbed by the acceptor. That would be consistent with the needed overlap in the emission and absorption spectrum. But when you dig into the physical details, you see that that's just not what's going on. Instead, you have a oscillating dipole in one molecule that you can capture via the transition dipole moment value, interacting with the transition, driving a transition in the other molecule that, of course, has a change in transition, that has a change in dipole moment involved in it. That change in dipole moment is described by describes the transition dipole moment of the acceptor. And so effectively what you're looking at here is a dipolar energetic interaction between the transition dipole moments in the donor and the acceptor. Now, because this is a dipolar interaction, it has an R-cubed dependency. That sort of came out in the background. We didn't talk... this did come out more or less when we looked at the electrostatic properties of a dipole. The potential energy of the electrostatic field of the dipole falls off as R-cubed. In this case, because we're looking at the interaction of the interaction of two dipoles, the interaction energy of two dipoles also falls off as R-cubed. And then the probability of the quantum transition between these two transition dipole moments is proportional to the square of that dipolar transition dipole moment interaction energy. So when you square this term, you basically get the r to the 6th power. So that's where that r to the 6th dependency comes off. So that's an important point. But another important point is that the efficiency of this transfer process depends on these dot products, right? So what are these dot products? This dot product looks at the relative orientation, looks at the magnitudes, but it also looks at the relative orientation of the dipole moments in the two molecules. This dot product looks at the relative orientation of the dipole moment, of the transition dipole moment in one molecule with the vector separating the molecules. Similarly, this is looking at the orientation of the transition dipole moment with the vector separating the two molecules. So what this means is, dependent on the spatial or relationship of the two molecules, right? Depending on the orientation, right? This term is a distance term, but now this is actually a unit vector. So this is a unit vector pointing between the two transition dipole moments. The distance is, of course, important. We've already captured the r-cubed squared, or net r to the 6th dependency of the transfer rate up here. This term now is looking simply at the orientation, right? We've now, up here, the probability depends on the magnitudes of the transition dipole moments and the distance between them. By the time we get down here, we have factored out, we're now looking at unit vectors. So we're looking at a unit vector pointing in the direction of the transition dipole moment, one transition dipole moment. This is the equivalent of the unit vector pointing in the direction of the other transitional dipole moment. Now the unit vector pointing between the transition dipole moments in the two molecules compared to the direction of the transition dipole moments in each of the two molecules. So what this shows is that the FRET process has a dependency on the orientation of the transition dipole moments, and therefore the mutual orientation of the two molecules. So FRET has, of course, a very strong 6th power distance dependency. It also has an orientational dependency. So depending on the orientation, the FRET efficiency can be much stronger. It can be much weaker. In a certain orientation, right, you will end up getting no FRET. Basically, if these two, so for instance, if these two dipoles are orthogonal to one another, right? If these dipoles point at 90 degrees of one another, the dot product will be 0. If the vector separating the dipole moments is also orthogonal to either one of these dot products, this distance, well, let's look up here for a moment, right? If these two dipoles are orthogonal to one another, that will be 0. If the vector separating is orthogonal to either one of them, this term becomes 0, right? And so basically, with completely orthogonally oriented dipole moments, you will have 0 fret. As those things reorient, you can then get much stronger fret. But the degree of fret depends on, of course, now 3 things. The overlap between the emission and the absorption spectrum. That's given by this so-called J integral. It depends on the distance. It's an r to the 6th inverse dependence on distance. And it depends on the orientation of the dipoles. So qualitatively speaking, these are the important properties of fret. We will use this in many different ways. The distance dependency we can use as a molecular ruler. Of course, the orientational dependency makes that molecular ruler, a little bit complicated and sometimes flaky. But fret, it can be nonetheless, it can be a tremendously effective molecular ruler, and it's an important phenomenon that's widely exploited in biochemistry and biophysics.